so much for joining us today. I just wanted to tell everyone a little bit about you before you got started. But Dr. Pedro Rodriguez is a PhD graduate from NYU in the Department of Politics. Pedro likes to explore the cognitive underpinnings of attitude judgments through the use of NLP, machine learning, and networks, and is very interested in studying the application of computational methods to the social sciences. Thank you so much for joining us today, and thank you for sharing about the work that you've done on the general channel of the Data Science Tip so we can learn more about what you're doing. We're looking forward to hearing from you today. And with that, please go ahead and get started. Thank you so much again.
Thank you. Thank you so much, Hara, for organizing this and for the space. Really looking forward to the feedback. So thanks everyone for joining and for being here. This is work in progress. We just recently made this paper public and recently released an R package based on this paper. So I'm really looking forward to getting some feedback on this. So as we all know, word embeddings became a hit when they were first introduced back in 2013. First by Mikolov et al. When they introduced word2vec, and then subsequently with Pennington's glove. And they became a hit in computer science, and then subsequently made a big impact in the social sciences. Political science, my discipline, not being an exception, where they've been used just as in political science, as in computer science, as feature representations for downstream NLP tasks. But also one of the bigger uses is to study semantics. So to study differences in meaning across groups and over time. However, embedding methods as they stand today have the limitations for this particular objective, to study differences in meaning across groups and over time. In particular, typical social scientists, we want more when we take methods from computer scientists. We want to be able to quantify systematic differences in meaning across groups and time and get measures of associated uncertainty, right? So this idea of uncertainty is something that is not necessarily inherent in the current existing word embedding methods. So essentially what we want for all intents and purposes is embedding regression, right? Something like multiple regression, where we can take the embedding of a given instance of a word, say immigration, for example, and regress it as a function of group covariates or time covariates, or any more sort of continuous measures. Here, immigration I is essentially just the embedding of an instance of immigration in our corpus, right? So this is what we're aiming for. This is what we want. However, this multiple regression won't work simply because each instance, each embedding of immigration R is not a scalar, right? So it's not that straightforward. These are vectors that vary in dimensionality, anywhere from 50 to, it can go well above 300. Usually the standard is around 300. So a natural alternative to this is multivariate regression. So something like this, where the dependent variable, the y, is a d-dimensional vector, right? So essentially sort of like where the d is defined by the dimensionality of the embedding space. And so are the coefficients, right? The betas are essentially d-dimensional coefficients, right? And each y is essentially an instance of, again, the word in our corpus, right? So this is sort of how it looks like. There's an embedding, a vector for a given instance of that word in our corpus. This is the full matrix of the dependent variable, d-dimensional again, and ultimately the y, the dependent variable, will end up being this n by d-dimensional matrix. This setup, again, requires that we can embed each single instance of a word in our corpus, right? So this is generally very challenging, right? So we turn to Aurora et al., a paper that they introduced this back in 2016, where they have this key theoretical result that essentially, if you have a word and you have a set of pre-trained embeddings, so embeddings that have been trained on a large corpus, you can essentially find the embedding of that word by taking the mean of the embeddings of the words around it. So you have a given target word, you just find the context around that instance of that word, you take all the embeddings, add them together, take the average, and that gives you the embedding for that particular word. So take, for example, this sentence. We're interested in the word bill, so we want to create an embedding for the word bill. The debate lasted hours, but finally we voted on the bill and so forth. We take a context window, usually symmetric window, around the target word. We find the context words, take the embeddings of those words from any pre-trained model, usually glove, for example, add those together, average them, and we get an embedding for that instance of the word, right? that actually, so just averaging, I sort of got you all excited about that, but that actually just by itself, just averaging embeddings like that just doesn't work all that well, right? We need to weight down prevalent but uninformative dimensions. So what happens when you just average these embeddings is that these embeddings share some common directions that aren't all that meaningful when it comes to semantics. And it'll be very clear when I show you the nearest neighbors that you get from the untransformed embedding. What I mean by this, essentially, that you need to downweight these prevalent dimensions, uninformative dimensions. So Kodak, the same people, subsequently suggest multiplying that mean by a transformation matrix, right? This transformation matrix, again, essentially just downweights certain dimensions and can be estimated just using a weighted regression. What this, I don't want to get into sort of the equations of it, but ultimately what this regression does is it takes a set of pre-trained embeddings, it takes a corpus, and for a given vocabulary, it just finds all the context, essentially minimizes the sum of square errors from the summing, averaging just the context words around the target words and the embedding observed in the pre-trained embeddings, right? So that's ultimately how this A, essentially finding the A that optimizes this equation here. This can be learned quite easily from a large corpus and only needs to be estimated once. So it's not specific to a given word, but it's specific to the corpus and the set of pre-trained embeddings. And so once you estimate this, each new embedding is obtained a la carte. Essentially, you can just, again, once you estimate A, just take your corpus, find the target what you're interested in, find all the instances in which it appears, all the contexts, add them together, average them, multiply them by this A, and that gives you a very good estimation of the embedding of that particular word. So why does this matter? Well, if we can produce an embedding for any word, we can produce them from any instance of a word, right? So, and that's essentially what we need for this embedding regression that we've been talking about. So does it work? Well, I'll show you some evidence based on the New York Times corpus of mentions of Trump. So these are two senses of the word Trump. One, the name Trump, with uppercase T, and the other just Trump with lowercase t. We'll see what comes out from that use of the word Trump. So we provide an a la carte embedding for each instance of the word, of these two senses of the word in this New York Times corpus. And the question is, can we separate the two senses, right? Does a method allow us, just by mapping these individual instances of the words, does it allow us to separate these two meanings of the word? So take an example here, the name Trump. Again, this is just taking a sentence from our New York Times corpus for this target word. We take the context around this target word, find the embeddings on a GloVe pre-trained model, right? And this is just using GloVe, the standard GloVe that you can just download from online. Take the embeddings of all these context words, average them, and multiply them by this transformation matrix, and we map them here. These are 300 dimensional embeddings. We use a dimensionality reduction to visualize it, so there's just for visualization purposes. We take another instance of that of the name in the corpus and map it here. Again, these are all individual instances. Now we take an instance of the lowercase t Trump and map it, and we see already in this even lower dimensional space that this is very different from the name, the two instances, at least so far, that we had from that name. Take another one of lowercase t Trump, and again, closer to where it should be, this different sense. We do this with just a random sample of 100 instances of each, and we see that indeed, just this method where we're just mapping, again, individual instances of these words is actually capturing the two senses of the word, right? So we found, essentially, this allows us to get at mapping those individual instances, which is a key component to be able to get to that regression framework. So just to show you that they actually make sense in terms of the nearest neighbors, right? So this is essentially grabbing all those red dots and all those blue dots, averaging those and finding the nearest neighbors. And this is the nearest neighbors for the name. Makes sense, President Trump related, former President Trump related nearest neighbors. And the Trump with lowercase t is related to a card game. Does the transformation matter? Well, it turns out that if you don't apply the transformation, you end up in this part of the space where you're surrounded by stop words, right? So this goes to that idea that if you're just averaging the embeddings without this transformation, you are augmenting certain directions that essentially aren't all that meaningful when it comes to capturing semantics. That's why the A is very important, right? So now we get to insert this into a regression framework. So suppose we're comparing the usage of a word by two different groups of people, group B and group C. And so our framework is essentially just like a multivariate regression, YI being just the embedding of a one instance of that word in our corpus, and group B being just an indicator equal to 1 if you're in group B and 0 otherwise. Again, this YI is a d-dimensional embedding. And so ultimately what this regression does is that it just essentially applies the a la carte method, the a la carte framework. The constant is essentially, again, just the constants of 1, and then the slope in this particular case is just an indicator capturing the group membership. And so if we just run this regression, this multivariate regression, what we're just doing is averaging each group's set of embeddings, right, of instance embeddings. And so the coefficients themselves capture the group embeddings, right, for that particular word. And so beta naught is going to be essentially capturing the a la carte embedding for group C for the word that we're studying, and beta naught plus beta 1 is going to be capturing the embedding for group B. Now the question is, how do we quantify essentially the group effect, which is ultimately one of the motivations for this work? Well, you can quantify it in various ways. The way that we suggest to summarize it is essentially just using the norm of beta 1, right? So the difference between the two groups is just captured. Something that captures is just the norm of this additional vector that you have to add in order to go from C to group B's embedding. The good thing about this framework is it's very easy and very efficient. It's not computationally very intensive. And so it allows us to do bootstrapping and permutation very easily. So we can do bootstrapping to get confidence intervals around these vectors. And so bootstrapping is essentially just imagine we have 100 instances of our term. We just sample with putting it back in, right? For bootstrapping, I forgot the word. And for permutation, right, is just randomizing group membership, right? And so that allows us to capture both confidence interval around these coefficients, as well as essentially a null to compare whether this is actually a statistically significant effect. And so we are able to quantify the uncertainty around this. So just to finish with a couple of examples, for example, there's partisan differences in political terms and then some stop words as a function of gender and party. We see that it's political terms clearly the norm of the beta hats. This is that group effect. It's the political terms that are most significantly different. And in particular, they're most different for party effects than they're more different between parties than within genders. So we can include multiple controls in that regression. We can do nearest neighbors, but in a much more systematic way. So it's not just finding nearest neighbors, but actually finding nearest neighbors and seeing whether they are statistically significantly closer or nearer to one group versus the other, right? So this goes from one end of the spectrum to the other end and just showing which are most significantly closer. This is for immigration to Democrats, and then those significantly closer to the Republican meaning of immigration. Finally, we can do this over time as well. So essentially just including indicator variables for time. And so this essentially gives you all the flexibility that you can get from a typical regression framework. We want to build into the continuous controls as well. We haven't done that yet, but ultimately that flexibility is there. Just to end, we built a software to allow you to do this and do this on your own corpus or corpora, and we try to follow a similar framework as the typical R functions like linear models and GLM. And so your formulas essentially take your word of interest and then your controls, your indicator variables, and then there's you can specify bootstrapping and permutation and so forth. You'll find both the paper and the package in my GitHub. So with that, I know I'm a little bit over time. I'm really looking forward to feedback or questions, and if given no time today, just feel free to, of course, reach out to me.
Yeah, thank you so much for that presentation. It was really interesting to hear how your approach differs from the previous ones. And I really love that you have a package that implements this. Like, it's not that we have to go and like read the paper and then try to parse out the little bits. Like, you've already provided that for us. I think that is so fantastic. I know we're kind of at the end of our time here that we had planned for, but I do see that there might be a question, and I would like to take a couple questions if that's okay with you, Pedro, and everyone else who is here. Let's see. And I'll just read this one question from the chat, but then everyone else can feel free to unmute and just ask your question. So the first question is from Lee, and he says, how do you calculate the norm if beta? Use L1 or L2? Lee, you might have to clarify that a little bit more.
It's a table, norm of beta.
Yeah, so the norm of beta is just the norm. It's just using the norm function of beta. But I think what you're referring to is in the case of nearest neighbors, whether we normalize, essentially whether we use L2 or L1. In other words, whether we normalize the inner product to get nearest neighbors, and there we use L2. So we do essentially what that means. We do normalize the inner product to get nearest neighbors.
Okay, and can you explain again? What is embedding here? I don't understand. How can you embed it?
We might, I was going to say, if you want to take other questions first, then maybe come back to that one.
Sure.
Longer answer, maybe.
Yeah, I can take other questions first and then come back to them.
I had a quick question. So are the when you are the betas themselves interpretable in any way?
Yeah, no, that's a good question. So the betas are essentially the embeddings, right? So the betas themselves are not interpretable in the sense of capturing, they capture meaning, but it's very hard to understand sort of what does it mean to, the norm of beta 1, right? It gives you, say, 0.5. What does that mean in terms of mean? Like, is this, so what that, it's ultimately, it comes down to having the ability to compare with other words. So for example, we always do comparisons. If it's immigration, we compare it to, say, another partisan word or stop words. And that allows us to, at a minimum, say, this is significantly different to, say, marriage, for example. And so this is a more polarizing term.
Could you apply it to other terms? You know what I mean? Much like, like the original, king versus king minus woman plus, man, woman. I'm getting it totally wrong. You know what I mean? Can you do that?
Yes, so I think something like that could make sense. So there's various ways that you can sort of get more meaning to this. So you can compare it to, say, for example, a given dimension on the space. So not a given dimension, but essentially define, say, the distance between male and female in the embedding space. How close is, say, this word to those two, right? So that's one way. And the other is, the one that we provide is essentially summarizing in terms of sort of a coefficient that people are used to in regressions, but highlighting that you need to essentially do it as in a relative way. So if you're going to study one word, compare this coefficient to that of another. I'm not sure. So I would have to think of what you're suggesting.
Does it give us like a filter? You know what I mean? Does it represent sort of a shift? That can be sort of applied, kind of like putting on the lens of that group. You know what I mean?
Yes, but so the beta, right? So the beta 1, right? So take this the simple example where you have the beta 0 and beta 1. So no more covariates. The beta 1 is capturing the shift, the additional movement that you have to do in order to, because again, beta 0 is the embedding for one group. Beta 0 plus beta 1 is the embedding for the other group, right? And so beta 1 is capturing that shift, exactly. It's capturing how much you have to shift. And so just one way of summarizing, because that's a d-dimensional shift, right? So one way of summarizing it is the norm. But yes, there's
it can apply it to sort of arbitrarily. And so like if you have like the shift for optimists, does that give you like the rose-colored glasses, the rose-colored lenses, put that sort of spin on any topics?
Yeah, that's something. It's the idea, the part of interpretation is something that we've been sort of thinking a lot about, how to actually make sense of all of this. That it's and also it's very easy in a regression framework, but this is slightly different. Right? So it's but yes, that's a very good suggestion. In terms of how do we embed these, we use GloVe pre-trained. So ultimately, you don't have to use GloVe pre-trained, but you need an embedding model that has been trained, right? And so ultimately what you do is you have your corpus, you have your pre-trained embeddings, you have a given target word that you're interested in, a set of target words, and you find the context in which these appear, and then you use these pre-trained models to embed those contexts and transform and so forth, just to explain. and that gives you the embedding. So we use these pre-trained models. In this case, we use GloVe. Potentially, if you have a very distinctive corpus, scientific journals, or it's a corpus in a different language, you'd want to train your own model if you have the data to train them, and then use that to do the a la carte embeddings. You'll have to compute the transformation matrix specific to that set of embeddings in corpus. I don't know if that answers that that question, but.
All right. Are there any more questions?
If there are any afterwards, feel free to reach out to me. This is, yeah.
All right. That sounds great. Well, thank you so much for coming. I'm taking a look
Thank
at your package right now on GitHub, because I'm thinking about maybe how we could get it into Python as well.
Yes.
We have a project that we want to grab this and use it for. But this is so great. And thank you so much for coming today and talking to us about your work.
Yeah, no, thank you, Shara, again for the invitation. And if you want to translate it into Python, I'm happy to work on that project as well.
Great. That sounds great.
Well, thank you all again for the time, and thank you for the space.
For sure. So after this, we have demos. I guess we'll start that in a few moments, but thank everyone for coming. And if you want to hear a little bit more about one of the projects that we're working on, you can stick around.
Thank you all.